Okay, so we're back here talking about the barycentric or X2 whirlpool map. So I'm starting from a point P0, and I'm going to be running this map upon a triangle ABC, so it's n equals 3. And as I run the iterations of this map, as we explained in the previous videos, you end up getting two terminal triangles, okay? So you're going to get a red triangle if you're running the iteration over the sides of ABC on a counterclockwise manner, and the green one for a clockwise manner, okay? Now what we did observe in one of our previous videos is that the two terminal triangles, they are at a ratio of 1/13 to the area of the outer one. So the area of ABC divided by the area of either red or green terminal triangles is this beautiful number 13. And we also saw that that ratio was independent of the shape of the triangle. So I'm only moving vertex C here without loss of generality. You get a distortion in the center, but the area ratio is immutable. Now, one way to explain this is via the affine group of transformations, right? If you pick a particular ABC, there is always an affine transformation that is going to take this system or send the system to a regular system. And in this regular system, it suffices you to analyze the geometry here, figure out that the area ratio is 13, so it should be preserved for any ABC chosen, okay? And as we said before, the two terminal triangles are independent of the starting point P0. Now, I'm showing down here a beautiful formula that was derived by Mark Helman, and that gives you this area ratio for any n-gon which is regular. So you know, this A sub reg here represents the area of a regular n-gon, and the A prime is the area of the terminal, one of the two terminal polygons, which is always going to be, is also going to be regular. It can be shown. Now what Mark derived was that for any n, okay, this ratio, it's 13 here, right, is going to be given by this formula. So if you actually run this formula, you're going to notice that you get this beautiful number 13, which is quite amazing. Let's go to the n equals 4 case, because I want to talk about this very interesting property of n equals 4. Let's go ahead and start from a, I don't know, without any loss of generality, an n equals 4 problem here, very similar. We already saw this in the previous video, that when you run both counterclockwise red or clockwise iterations green, you get these two terminal parallelograms shown red and green here. And not only is this quite surprising that they are parallelograms regardless of the shape of ABCD, you get two parallelograms. Their vertices lie on an ellipse, this pink ellipse here, but also the area ratio between the area of ABCD, the outer polygon, or quadrilateral in this case, and the two inner ones is this magical number 5. Now, this is also verified by this formula, but what's weird here is that there isn't, in general, an affine transformation, okay, of any given quadrilateral, okay, to the square or regular quadrilateral situation, right? So if you analyze the regular quadrilateral, you do get this area ratio, you get these two terminal squares, okay, and they lie on a circle, their vertices lie on a circle, and the area of ABCD divided by the area of either one of these terminal squares is 5. Now what's surprising with the quadrilateral is that even though you can't use the affine argument here, okay, this area ratio is independent of ABCD, okay? Now let's go back to Mark's formula. If you actually plug in n equals 4 here, you're going to get that this ratio is exactly 5, okay? All right. Now let's try to explain why that is. Why is it that in the absence of an affine regularizing transformation, this area for ABCD, the area ratio is independent of ABCD? Okay, so here's what we discovered. Let's go to the n equals 5 case. Okay, now let me start. So you can see here that the area, maybe this should be called area divided by a prime, so that we keep the, let me cancel that. Imagine that this area divided by a forward is really a divided by a prime as of previously, okay? Now I'm showing here the n equals 5 regular case. So this is a regular pentagon, and if you apply that to Helman's formula, you're going to get exactly this number here, 3.11146. Okay, you can actually get an exact algebraic an expression for it. But look at what we found out. So before I get there, I'm doing the exact same thing. I'm running one counterclockwise red and one clockwise, one that is counterclockwise red and one that is clockwise the green, and I'm getting two terminal regular pentagons because I started from a regular pentagon, so their vertices are going to lie on a circle because everything here is regular. But this is what we discovered. If we start from this number here, 3.11146, I noticed that if starting from the regular configuration, I only perturbed one of the vertices, okay, one of the vertices, regardless of which one, okay, the area ratio is preserved. So if I keep the other four vertices in this case in their original regular configuration, notice that I'm not changing A, B, C, or D, only E, okay, the area ratio is preserved. Let's go back to the regular configuration. Let's move now, for example, vertex D. You can see here that the area ratio does not change if I'm only perturbing one of the vertices away from its regular location. Okay? Now, if I perturb a second vertex, then the area ratio changes. Okay? So the requirement for the previous observation to be the case is that I only perturb one vertex, for example, C, away from the regular configuration. Now the algebra works out, and we do have now closed form solutions for the two terminal polygons in general, for generic starting polygon. We derived those. They turn out to be like a linear system, an n by n linear system. Okay, but if you do that, you can show that the perturbation of just one vertex out of the original regular configuration doesn't change that. So why does this help us with n equals 4? I'll ask you for just 1 second. Let's go to the n equals 6 and verify that that's true there as well. So here's an n equals 6 whirlpool. I start from P0. I have the counterclockwise and clockwise iterations. Okay, they both result, and if I change this color here just for our own consumption, I'm going to make this dotted, and I'm going to make this dotted, okay, like so, so that we see that there's two terminals and there's two iterations that end up in those terminals. You end up getting, what are you getting here? You're getting 5/3, right? So if you're getting, is that correct? Or 7/3? Yes, you're getting 7/3 as the ratio here, and you're going to get that ratio if you actually run this formula down here for n equals 6. Now, as we said before, look at the property. I'm looking at the regular hexagon here. I'm just going to slide some random vertex, for example, E, away from its regular location. I'm perturbing E here. Notice how the area ratio does not change. It's still 7/3. Okay? Now, if I start moving, for example, some other vertex, B, for example, or C, okay, you can see that that area ratio is changing because now I have two vertices that have been perturbed away from their regular configuration. So if I go back to regular, I restore the 7/3, and then I can now start moving F. I got the same thing. If I restore it, I start moving C. I got the same thing. Okay, so we notice this very interesting phenomenon here. Now, why does this help us understand why n equals 4? Let's go back to n equals 4, is independent. The area ratio here is independent of A, B, C, D. Why is that? Because let's think of it that way, okay? We're going to start. So keep in mind this regular configuration where the area ratio is 5, and now let's consider a non-regular configuration. Something like that, A, B, C, D, okay? Some general position of a quadrilateral. You're still getting the ratio of areas equals to 5, and the miraculous thing here is that it does not depend on A, B, C, D. Now, why is that, and how can we use the previous argument to show this? For a moment, ignore D, and let's only focus on A, B, C, okay? Let's just focus on these three vertices. Do you agree that there's an affine transformation that will send A, B, C to two sides of a square, namely A prime, B prime, and then a B prime, C prime that is perpendicular to A prime, B prime of the same length? So just keep in mind that affine transformation that will send C, will actually send A, B, and C to the two sides of a square, the two consecutive sides of a square. That is easy to show that that always exists. Now, wherever D is sent under that transformation can be regarded as a perturbation with respect to its position on a regular quadrilateral. So wherever D is sent under such an affine transformation can be regarded as a perturbation of one vertex of a regular polygon with respect to its original regular location. And we just saw in the cases of n equals 5 and n equals 6, and this can be proved algebraically, that when you just perturb one vertex of whichever n configuration, for example, n equals 6, if I just perturb one vertex, okay, the area ratio doesn't change. So what we're doing with n equals 4 is that if we go away from the regular configuration, okay, and we notice that the area is not changing, it's because there's always an affine transformation that converts A, B, C to two sides of a square, and wherever D is sent to is a perturbed fourth vertex of that regular square, regular quadrilateral. Okay, so this proves that the area of the terminal polygons, the ratio of the areas here, is independent also for the n equals 4 case of A, B, C, D. This is no longer true for any n greater than 4, right? So the area of a, say an irregular pentagon, okay, depends, you can see the area ratio here, okay? This area ratio will depend on the position of all the vertices, okay? The only exception here being in the case that you start with a regular configuration and you only perturb one of the vertices away from that. Okay, so I guess that concludes this video. See you on the next one.